Okay. All right, so we're on for part 2 of this. Okay. Okay. So, I really wish I should have done this on this one so I can show it. Okay. So now I'm going to talk about the life cycles of stars.
I already know about the life cycle of the star. You're going over the things I already know.
So we're going to split stars into kind of 2 categories. There's low mass stars and massive. And these low mass stars, this is going to be from 0.08 solar masses, so 0.08 times the mass of the sun, to about 8 times the mass of the sun. So this lower limit, this 0.08, why can't stars be less than that? So we talked about how when a star is forming, this gas cloud is condensing down and the inside starts heating up. And eventually the core gets hot enough that this fusion can happen, can start turning hydrogen into helium. And the core temperature increases with mass. So if you have more mass to start off with, you're going to be able to get your core hotter. If you are below 0.08 solar masses, your core is never going to get hot enough to start fusion. So you can have this gas turning into a ball, but its core is never going to get hot enough to start fusion, and it just stays as a ball of gas. So you have like gas giant planets, or like brown dwarf, which are kind of failed stars. They tried to be a star, they couldn't get hot enough on the inside, and they just weren't able to start that fusion up and become a star. So if you're less than 0.08, you can never get hot enough in your core to start fusion. And then up to about 8 solar masses. So both of these stars start out on the main sequence. Both these massive stars and the low mass. And they are burning hydrogen into helium in their cores. Okay, these guys, they don't stay as long in this stage, right? These guys can stay a long time in this stage. These guys don't stay as long, they go through it faster. But they both start out here and they both spend some time there. So then, once all of the hydrogen in their core gets turned into helium, they like start to run out of fuel a little bit. Right, they can't burn any more hydrogen at this temperature. So in order to start burning helium, they need to heat up. So they get a little bit hotter. And we talked about in class how the hydrostatic equilibrium of a star is what keeps it in its shape. You've got gravity pulling in, and you have this thermal pressure pushing out. So as the core gets hotter, this thermal pressure gets bigger. And the thermal pressure becomes a little bit stronger than gravity, and so the star expands until it gets to equilibrium again. So it gets bigger, the outer layers, this atmosphere of the star just kind of puffs out. And this is the red giant. So the core gets hotter, the outer layers puff out and cool down. So when we look at this star, it looks cooler to us because we're seeing the outer layers. So it's up in that colder side of the HR diagram, but the core is actually getting hotter.
So red giants have the hottest core.
They have a hotter core than the main sequence. So in this core, they are turning helium into carbon. And then, so you've got helium into carbon in the core, and then this little layer out here of hydrogen. This has gotten hotter, And this hydrogen that's right near this super hot core, this heats up, right? If you're right next to something really hot, you're gonna get hotter. So this gets hot enough that this shell here is able to start fusing hydrogen into helium. You helium into the carbon into the core, and hydrogen into helium in a shell. And then eventually they turn all their helium in the core to carbon. And then some of them can do a little bit of turning carbon into nitrogen and neon and oxygen and a couple other stuff, but they don't get much farther than carbon. And then they say, okay, well, we gotta try to get a little bit hotter to burn a little bit more to maybe make to turn this carbon into nitrogen and other stuff. So this temperature heats up, and just like what happened before, as the inside heats up, that thermal pressure gets bigger, so it puffs out even more, except at this time, it puffs out so much that these outer layers just float off into space. And this is the planetary nebula. So you've got this core of the star, and all the outer layers are just floating out into space. And we have those really pretty pictures that he showed us in class of all this gas from the star that surrounds this hot, hot, hot core, right? So the core heated up to here, and at this point, there's no more fusion. It can't get any hotter in the core, so it can't do any more fusion. And what's left, as in the middle of this planetary nebula, is a white dwarf.
Does the white dwarf have a high surface temperature?
It starts off at a high surface temperature. So it's, remember this core got super hot, and then all of the stuff around it floated away. So you've got this super hot core, but it doesn't have any fusion anymore. So there's nothing to keep it hot. So it starts off super hot, and then it starts to cool down. It's like a coal. It's not burning anymore, but it starts off really hot, and then over time it gets cooler and cooler.
So the white dwarf is in the center of the planetary
Yes.
nebula? And the planetary nebula is basically like the red giant, but the core got like the thermal pressure got even bigger.
Mhm. And so all the, you've got the atmosphere of your star here. This just kind of floats off into space.
Oh, so it's the process of the outer layer.
Right. That's the planetary nebula. So the outer layers just detach from the core and just drift off into space. And by drift, they're going pretty fast, but yeah.
Can I try to explain or re-explain to reiterate? So, and I guess I don't know the order that this happened in, but is it helium to carbon in the core first, or is it hydrogen to helium in the shell first? Or is it happening simultaneously?
They're not going to happening at the same time.
Okay, and that's for, you said, stars that have 8 or less massive sun?
Yeah, this is going to happen for both of them, but these guys are going to keep going.
Okay, and then is it when they get hotter that they can do helium to carbon in the core? Or
Yeah, they have to get hotter to do the next, for every step. Every time you take your old product and you make something new with it, right? So initially we were turning hydrogen into helium. If we want to take helium and make it into carbon, we have to get hotter. If we want to take carbon plus helium and make that into nitrogen, we have to get hotter. If we want to take that nitrogen, turn it into oxygen, we have to get hotter.
And how does mass have to do that again? Because if it has more mass, it burns through quicker or something?
Your maximum temperature is based on your mass.
Okay.
So these guys can only get so hot in their core.
Oh, okay, but once it's bigger than 8 times the mass, it's like,
Right, then they can get hotter. So these guys can only get hot enough to burn a little bit of carbon. Yeah, so then these white dwarfs. So you get hotter by increasing your pressure and getting smaller. But these guys can't get any hotter because white dwarfs are like as compressed as they can be. They are held up by something called electron degeneracy pressure. So there's no fusion here. There's no fusion. So this is the atoms. This is not really what's happening. Atoms are really weird. But you can think of it like the atoms in this are like shoved up against each other. They can't get any closer. They're pressed up against the sides of each other. Yep.
Do you think we're gonna have to know electron degeneracy, blah blah, or are we just gonna be able to, if we remember electron, like is it gonna be more multiple choice or? Do you
Yeah, something like this would be multiple choice question.
Okay.
So if you can remember, white dwarfs, electron degeneracy, what's the math? Yeah.
Sorry, I just want to, okay, so the core is doing its thing. If it's less than 8 times the mass of the sun, it can do a little bit of carbon in there, and then it has its helium shell,
Mhm.
the helium and hydrogen fusion, and then as it's heating up, it's like spreading it out more, and then it like,
Right.
and then it makes the nebula, and does it keep on doing more like shells?
No, so at this point, it can't get, like this nebula happens when it's used up all of this fuel. And it can't burn this anymore. So it heats up to try to burn more, but it doesn't get to a point where it can burn anymore.
So it just like,
So it just stops burning. It's like a coal now in the middle. It's not on fire anymore, but it's still really hot because it was on fire 10 seconds ago.
and then just slowly begins to
And then
cool
it
off
just
and
cools down over time. So, a star like the sun, it starts off here on the main sequence and it lives its life here. And then once it's done on the main sequence, when it burns up all its hydrogen, it goes up this way to the red giant. So the inside is getting hotter, but the outer layers are getting cooler because they're getting farther away from this hot inside. So this is surface temperature. So the outside cools down and it goes up here. And then it sheds off these outer layers. So all of a sudden we're looking at this hot core. And so it heats up. And it goes this way. As these outer layers go away, it heats up over here. But it's still just this little white dwarf core. It's not part of this main sequence. It's just kind of over in this same area. And then it just starts to cool off and it goes down this way. So all of these little white dwarfs, as time goes on, they're all moving down this way. They're all cooling down, getting cooler and less luminous.
then they just disappear, or what?
Eventually they turn into what's called a black dwarf, but they don't exist yet.
Because it hasn't been enough
It
time.
hasn't been enough time, yeah. So there's a question that says, why don't we have any white dwarfs that are less luminous than like this luminosity? And the answer is, our galaxy was formed a certain amount of time ago, like a finite amount of time ago. And then the first stars formed inside that and lived their lives and turned into white dwarfs. And they're getting cooler and cooler and cooler as they go down and less luminous. But there just hasn't been enough time for anything to make it down here.
So none of them have lost all of their heat.
Right. There's just not enough time to have made any of these what they call black dwarfs. And these white dwarfs, so this core is essentially like super, super dense carbon. So they're basically giant hot diamonds in space. Yeah. So white dwarfs are pretty interesting. Okay, so you guys feel okay about low mass stars and their life cycle? Got it now. Woo. These 4 steps. So there's these questions. Question 17, which of the following are true and which are false about the white dwarf the sun will eventually become? It will have become slightly more massive than the sun is now because lightweight hydrogen has been converted into heavier helium. Is that true or false?
What number was that, sorry?
This is 17. So this is false. So remember, as this fusion happens in the main sequence, every second it loses a little bit of mass, right? Because you get 2 hydrogens turning into 1 helium, and a little bit of mass turns into light, turns into energy, and comes out as light. So it loses a little bit of mass every second.
It's false, right?
Yeah, so that one is false. And then also, right in this stage, like half its mass just floats off into space. So the white dwarf is a lot less massive than the original star was.
I have another question. I think it's a like the obvious one, but I just want to check. The red giants have a lot of mass, right? 'Cause
They have the same amount of mass. It's this same amount of mass as the original star. It's just puffed up.
More area.
Yeah.
Not being held.
So it's less dense. It's the same amount of mass, bigger volume, so they're less dense. So all the mass inside is spread out.
I'm really confused, or I don't really know the context of the answers for 18, which is which of the following support the theory of supernova to core collapse?
Okay. That's more massive stars, so I'm gonna get to that in a second. So for B, it will be enriched in helium compared to the sun. Is that true? False? It's true. We've got helium is being made in these stars, so they're gonna have more helium than the sun did. It will initially have a much higher surface temperature than the sun. This is true, right? So it starts off, when it starts on its red dwarf or its white dwarf journey, it's like over here, so it's hotter than the sun. Because it used to be, the inside had to heat up a bunch and then cool back down. And it will be supported against gravity by electron degeneracy forces. Yes, that is true. Okay, so there's another question that says, check off which one of these the sun goes through. It's like question 3 or 4.
Quick question. Was A false?
Yeah.
A is false. It is losing mass every second as there's fusion, because the light from the sun used to be mass. Gets turned into light, and then in the planetary nebula stage, it loses like half its mass. Yeah, so question 2, the sun will eventually go through which of the following phases? Planetary nebula, check. Red giant branch, check. White dwarf, check. Supernova 2, that is not in the low mass stars life cycle, so that's a no. So then,
Sorry, white dwarf, yes.
white dwarf, yes. So massive stars, they go into this red giant branch, and they do the same thing. They burn helium into carbon in their cores, hydrogen into helium in their shells. And then once they've got a core full of carbon, then they're like, well, I have enough mass. I can get hotter. So they get hotter, and they start burning carbon into other stuff in their cores. And then in their shell, so they had helium to carbon in this core, and then hydrogen to helium in the shell. And then as they get hotter, they get carbon into other stuff in the core. This all turned into helium, but it's hot enough now that this helium gets turned into carbon. Now this shell outside heats up, and this hydrogen can turn into helium, right? So this is at one time, and then this is a little later. Right, so these shells kind of go outwards. So this keeps going. Carbon turns into nitrogen, turns into oxygen, turns into magnesium, all sorts of stuff, all the way until you get to iron. And the thing about iron is, so all the other ones, when you take 2 hydrogens and you turn it into a helium, that releases energy, right? That creates energy. When you take iron and try to turn it into anything else, that uses up energy. So this star is not going to take iron and turn it into anything else. It's not going to waste its energy turning iron into something. It wants to send its energy out as light. So this iron just stays there and starts to build up. And it builds up this iron core as all the other shells start turning stuff into iron. The iron collects in the middle, and you get this bigger and bigger and bigger iron core until you get to this iron core.
In the second diagram, in the core, that's carbon goes to.
This is nitrogen first. It's really not important. I think they stuff you guys know. You need to go helium or hydrogen to helium, helium to carbon, and then carbon dot 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 iron. So you need to know that carbon turns into other stuff. Eventually, you get iron, and iron is where you stop. And you can't turn iron into anything else. So this iron core builds up and it builds up and it builds up, right? And once you get to 1.4 solar masses for your core, so as this iron core is building up, it's getting more and more gravitational energy, right? It's getting more mass, so more gravity. But it's not fusing, so it's not able to produce that thermal pressure outwards. So eventually, you get so much gravity from this mass that this iron core is like, I can't take it anymore. I'm just gonna collapse in on myself. And in like a fraction of a second, this big iron core just collapses down to this tiny little thing. And so remember I talked about how for electrons, I said, you know, this is almost about as tight as they can be. These atoms are right pressed up against the edges of other atoms. What happens here is basically these atoms are broken into pieces and shoved together even tighter than what they were before. So, but the way that this happens, if you've got your iron core and your atmosphere of a star here, and then in like 1 second, your iron core collapses down into something this tiny. It used to be this big, and now it's this big. Then all this atmosphere is going to rush in to fill this space, right? This is like this empty space that gets just created as this core collapses.
Like a vacuum.
Right, and all this atmosphere rushes in to fill it. And it hits this super, super dense iron core, and it just bounces right off. And it bounces off so fast, this is an explosion. And this is a supernova.
It's light, right? Or like energy.
This is mass. This is the gas that made up the outside. This rushes in and then just explodes back out.
So all of the gas that's left that's not iron.
Right. And then when this happens, there is some shock waves that are created. This is going so fast, it creates shock waves, and that heats things up. And so you actually get some more fusion out as this stuff is getting blown out. And yeah, but so this iron core collapses down, the atoms like break into little pieces and shove even tightly more together. And all the stuff on the outside gets blown out. This is a type 2 supernova. So that's there's like 2 questions on the homework that talk about type 1 supernova. We're not gonna cover those in the quiz because we didn't go over them in class. They're a different mechanism. Type 2 supernova is core collapse.
And does it just keep bouncing back and forth?
No, it just bounces in and then just gets thrown out so much, it just gets thrown out into space.
And what happens there?
So all that's left is what's called a neutron star. So a neutron star is this collapsed core. And that's what's left behind. And this is held up by neutron degeneracy pressure. That one's pretty easy to remember, right? Neutron star, neutron degeneracy.
So is that how like black holes are created?
So black hole is if you get even more mass, like if black holes are like the biggest mass star, and so this neutron, if this collapsed, instead of collapsing into a tiny little core, it just kept collapsing and collapsing until it was like one single point that had all of this mass. That's a black hole. So this core, this is now, you took this giant star, this like 8, 10, 50 times the mass of the sun star, and you collapse its core down to the size of Santa Cruz. Like, these are so dense. These are the most dense objects, and they're spinning really, really fast. So there's this idea called the conservation of angular momentum. And if you have something that has a big radius and it's spinning, if you decrease the radius, you're going to increase the spin rate. And you can see this with ice skaters, you can see with other stuff. You can see it. I don't know if it's going to work. It's hard because I'm wearing a dress. Someone want to come spin me?
I'll spin you.
Okay. So, I'm in this chair. She's gonna come spin me. Let's see if this will work. Better with like a stool. Okay, spin me.
It's kind of like a rock.
Okay, well this is not gonna work. The point is, if she's spinning me and I throw my arms out, I'm gonna slow down. It's the opposite. If I pull my arms in, I'm gonna speed up. So you have this star is rotating. This core is rotating. It collapses down. Radius gets smaller. Spin rate gets faster.
And is the process that you just explained, like, it at some point exploding, is that similar to the?
Not really. The Big Bang was more everything coming out of nothing. This is just stuff going in, hitting a wall, and getting thrown back out. Yeah, so all of this is it all used to be the atmosphere of this star, and it's getting thrown out. Okay? So, yeah.
So what is the reason behind the answer for 21, especially the part that it says a large ratio of the radius of the iron core that collapses?
So why do we expect a freshly formed neutron star to be rapidly rotating? So conservation of angular momentum tells you that if you decrease your radius, you increase your spin rate. So this iron core used to be a certain size, and it was spinning because stars spin, and then it collapsed down into this tiny little thing. So it's going to spin really, really, really fast because it went down to a tiny little size.
What number was that?
That is 21. So then 19 or 18, which of the following support the theory of supernova 2 core collapse supernova? So A is supernova 2 are always seen near regions of star formation. And this is true because they used to be stars, right? So, a supernova used to be a star, and a star is formed in a region of star formation.
Is there a lot of space in space that are not
Yes,
inhabited by stars?
yes.
What does B mean? Of heavy evidence of heavy elements in galaxies?
Yes. So the supernova remnants in the galaxy show evidence of heavy element enhancements. That means that they're not just made up of hydrogen and helium. They're made up of all these other things, these other elements that were created in the middle in all these steps before they get to iron.
It's just the wording though.
Yeah. So these guys, this makes these, and then that gets shot out into space. And then also, as this heats up, sometimes you get even more fusion and even more stuff gets created.
That's true.
Yeah, that is true. See, there are pulsars rotating neutron stars at the center of some supernova 2 remnants. That is true.
But it is just some,
Some of them have black holes.
but it's one or the other.
Generally, yes. Yeah. So I will talk about black holes later in the class, I'm pretty sure.
Wait, what are pulsars?
Pulsar is a rotating neutron star. So all neutron stars rotate. A pulsar just happens to have, so as these neutron stars rotate, like you've got this star and it's rotating, and then these like jets come out. And if the jets come out like in this direction, like so it's rotating and then the jets are coming out like this side, then if I'm rotating and my arms are the jets, like you're gonna see these flashes, right? Because you only see it when the jet is pointed right at you. So it's kind of like a lighthouse. So we saw these things that were like these flashing stars. We're like, what the heck is that? And it's just a neutron star that the jets are pointed at us.
Are all stars rotating?
Yes.
Oh, is that why they?
They twinkle because of atmosphere. Yeah. The air in the atmosphere just kind of shakes the light up and makes them twinkle.
Would D be false?
D, they have luminosity similar to red giants. Yes, D is false. Supernovas are much more luminous than red giants. This is like crazy bright. You can have one supernova that is as bright as the entire rest of the galaxy.
But they only last for a second. Once they become neutron stars.
So they last, they are at their brightest and then they fade over time. So this was a question that they asked for a long time. They were like, why don't they just get bright and then go dim? Why do they fade over time? And this has to do with this gas out here is radioactive. This gas that gets shot out is radioactive and it decays and that creates energy and creates light. So that gives off more light as time goes on. But they have like a peak luminosity and then they get dimmer from there. Right.
They're the two.
Yeah. So that's the supernova. So which of the following are predicted properties of the neutron star left behind by a supernova 2? They will initially have very high surface temperatures. That is true, right? They had to get super hot to burn iron, to make iron.
Which question is this?
This is 19. They will be spinning very rapidly. That's true. That's that conservation of angular momentum. They're spinning super fast. They will have a much higher density than main sequence stars or white dwarfs. That's true. These are like the most dense things that you're going to get.
All of this stuff, right?
Huh?
All of it's compacted because of it.
Right. Right. Like, and it's not even like, so electron degeneracy, this is like carbon atom pushed up against carbon atom. Neutron degeneracy, this is like they've broken these atoms up into pieces and are shoving like their neutrons up against
Like
each other.
how sand can be much more
Right.
densely packed than rock.
Exactly. You took these, if these were rocks, now you've crumbled them up into sand and shoved them together even tighter.
Can we go over 14?
Yeah. And then D, yeah, they will be supported by gravity against gravity by neutron degeneracy pressure. That is true. And then you got a question? A for 18 is true. They're senior regions of star formation. They were stars, so they exist in the areas where stars are made. Right? Because stars don't like really get born and then just go and like live off their lives somewhere else. Generally, they're born and they live and they die in the same place. So you wanted to do 14?
Yeah.
So how much energy is released by the reactions in the core of the sun each second? So I've told you, maybe not today, but in this homework for sure, that the luminosity of the sun is 3.9 times 10 to the 33 ergs per second. So this tells me that every second, the sun is giving off 3.9 times 10 to the 33 ergs, right? It gives off 3.9 times 10 to the 33 ergs in 1 second. And where does that light come, where does that energy come from? Diffusion, the nuclear reactions that are in the core. Right? So if this is 3.9 times 10 to the 33 ergs per second, how many ergs in 1 second? Right, 3.9 times 10 to the 33. Right, this is this many in 1 second, so in 1 second you have this many ergs.
Luminosity is the results of the energy
Right.
being used.
Yes, luminosity is how much energy is giving off every second. That energy comes from these nuclear reactions.
That, why would it ask us that if you said that's gonna be given, right? 3.9 times 10.
This is going to be given, but I want you to be able to connect this, the luminosity of the sun, how much energy the sun gives off. Where does this energy come from? From the reactions in the cores.
Okay.
And yeah, and this is an energy per second. So it's just in 1 second, it's just this much energy.
And did you say that's one solar luminosity?
Yes, this is,
I mean, even though it's kind of random, but.
yeah. Ergs per second is 1 solar luminosity.
And then the energies that come from the fusion at the core.
Right, because the sun right now is on the main sequence. It's about halfway through its time on the main sequence. So it's been there for about 5 billion years, and it's going to be there for another 5 billion years. Yeah.
Would this question be more correct if it actually told us that this was on the main sequence?
So it's asking about right now in the sun, and the sun is right now in the main sequence. So unless it asks specifically about a different fate time, like a different place in the sun's life cycle, like there is one question that says, you know, when the sun becomes a white dwarf. But unless it asks something specifically, assume that we're talking about the sun right now, and that is the main sequence sun. Guys have any more questions? Any more of these problems? Yeah. 20? Yeah. Okay, so 20 is about supernova type 1, and that is not something we covered in class, so that is not going to be on the quiz. Yeah.
Number 22.
The lowest luminosity white dwarfs in the galaxy have about 10 to the -5 luminosity of the sun. Why are there no white dwarfs at luminosities longer than this? They just haven't had time to get cool in it, to get they're getting less luminous over time, but there just hasn't been enough time since the galaxy was created, since the galaxy formed, for them to get cool enough. Yeah, no, go. Feel free to email me. I'll be answering questions tonight. I'm gonna just as soon as I get back to my office, I'm gonna post a couple more. I have some more of these ratio problems that I came up with and worked out, so I'm gonna post those so you guys can see those. I'm gonna try. Don't hold me to this, but I'm gonna try, if I can figure it out, I'm gonna try to screen record me working out all the math problems and post that. I know it's like a day before the quiz, but I'm gonna try to get this up tonight if I can figure out how to screen record on here. But yeah, if you guys have any questions, just shoot me an email and I will do my best to answer it. Okay. Thanks, guys. Huh? Oh, yeah. What else am I gonna do? Yeah, but this, like, they have a backup generator for these buildings, so there's always power here. Yeah. Like a lot of the other grad students, like I have power in my house, but a lot of the ones that don't have power were coming here to like shower and stuff because ISB always has power essentially.
So cheap. Oh wow, you sort of agree with what I had. Thank you.
Okay.
My God.